Okay, this first one says that it's a calculator problem, but not so much a calculator problem. You kind of need a calculator, but you could actually do this without one. They say if the series S equals that series from 1 to infinity, it's an alternating series. That's what this little alternating series term does. And then 1 over n times 2 to the n. So that's approximated. So this is the infinite series, right, which actually equals the function, whatever function you're approximating. Well, usually, but in this case, this infinite series is approximated by a partial sum. So this infinite series of infinite terms is approximated by the first k terms of the series. They say what's the least value of k for which the alternating series error bound guarantees that the actual value minus the approximated value, absolute value of that is less than or equal to 0.0005. Okay, so first off, this absolute value of s minus sk is just the error, right? You have an approximation, it's not exact, so there's some error, some amount that you're off from the actual value. And the alternating series error bound, this is an alternating series. They say that the error bound says that this error is always less than or equal to the first unused term. So let's say k is 6. So if you're estimating this infinite series by the first 6 terms, then the error is going to be less than or equal to, or that the absolute value of the difference is going to be less than or equal to the absolute value of the first unused term, the 7th term. Okay, so let's see. So down here I put not including the part that makes the signs alternate, but just the nth term itself. So I put that in the calculator as y1. And I just made a table of values, just starting with the first answer choice. And actually, I could have really started with 7, but okay. But so we want to see what's the first. We want to see what's the first value that's less than this, right? Because if we get a value, if we know that the error is less than a number less than this, then it's going to be less than this also. So we want to see what's the first number that's really less than this. And so if you go down here, so if you notice at x equals 8, oops, 1 second. So at x equals 8, okay, that's really for us, that's when k equals 8. So at k equals 8, that's 4.9 times 10 to the negative 4th is 0.00049. So notice that's just a little bit less than this, right? 0.0005, this is 0.0004. Okay, so this 8 represents the first unused term. That means if we're going to use this as the error, then our partial sum is going to be the first 7 terms, right? So if this is the 8th term, if we're calling this the error, if this is the first unused term, that means the first 7 were the used terms in the approximation. Okay, and that's it. So you notice this 7 when k is 7. That's not small enough, 0.001. That's bigger than this. So yeah, so this is the first term. Yeah, so that's got to be, this is the first unused term has to be the 8th term. So that means our approximation has to use the first 7 terms, and that's what k is. K is the actual approximation itself, not the first. The first unused term is the 8th term, but it's the approximation of the first 7 terms, and that's what they asked for. So okay, so that'll be B. Okay, so this next one is talking about which of the following series can be used with the comparison test. Sometimes they we'll call it the direct comparison test. So if you see comparison, that's the same thing as direct comparison, as opposed to limit comparison, which is different. So can be used with the comparison or direct comparison test to determine whether the series converges or diverges. Okay. So first we have to have some instinct about whether this converges or diverges. We can see that this is going to converge because this 4 is a constant. This sign n is basically a constant. We can treat it like a constant since it's bounded. This sign's range is from -1 to 1. So sine of any number, doesn't matter what number, can't be bigger than 1, can't be less than -1. So basically this top, if sine's between 1 and -1, then when you do 4 plus sine, that's going to be between 3 and 5. So this top is just some number between 3 and 5, at any point for any given value of n. Okay, so the top's basically a number, and then you have a number over n squared. And so, this is kind of like a p-series. You got some number over n to an exponent. And the p-series test tells you that if the p-value, which is the value of n on the bottom, the exponent of n on the bottom, if that's bigger than 1, then it converges. If it's less than or equal to 1, then it diverges. Okay, so since this is bigger than 1 and the top's a constant, we know that this is going to converge. Okay, so, but we still have to use the test to kind of formally figure out which one of these that we're going to directly compare it to. Okay, so we know we're going to compare it to some kind of n squared. So we know we can cancel out that and cancel out that. Okay, because it's got to be kind of similar to this in a way. Sometimes we'll simplify this and then compare it, but this one, we just compare it to one of these. So the fact that this converges, we want to compare it to a function that's bigger than this always for any value of n. Technically, it's for any value of n past a certain number. But we'll just say for any value of n. So as long we want to figure out one of these, whichever answer choice, is always bigger than this. So if we can figure out a series that's always bigger than this, and it converges, then this smaller one has to converge also. Right? If a bigger series converges, then anything less than that has to converge also. Any one that has terms that are always less than it has to converge. So that's the idea. So notice if we compare it to C. So this, we realize this top, 4 plus sine, since sine's between 1 and -1, this top's between 3 and 5. So just compare it to this series. So this will always be bigger. 5 over n squared will always be bigger than 4 plus sine over n squared. So that's the function we'll use. Okay, next one, they say which of the following series can be used with the comparison test. So remember, this is when they say comparison test, they mean direct comparison test instead of limit, to determine whether the series converges or diverges. Okay, so we have an instinct that this will diverge because this 5 won't matter. When n goes to infinity, you adding 5, think about it, at some point this n is going to be a billion and then a trillion and then a Googleplex. It's going to be really big, and adding 5 is meaningless. So even multiplying by 2 is meaningless. So you can kind of get rid of the 5 and get rid of the 2 and realize this is kind of like n over n squared. Okay. And n over n squared simplifies to be just 1 over n. Okay, and since 1 over n diverges, you can think of it, this is the harmonic series. Just memorize that the harmonic series diverges. You could also think of it as a p series, where p is 1. Right, the exponent in the bottom, the exponent of n is less than or equal to 1, so it diverges. Okay, so we have some instinct that since this kind of simplifies to be 1 over n, if we get rid of the constants, that since this diverges, this is going to diverge also. Okay, so the fact that we have an instinct that this diverges, we want to figure out, we want to compare it to another series that diverges also and is always smaller than this. Because if we can figure out one that diverges and always is always smaller, if it diverges, it goes to infinity. So if you figure out a series that goes to infinity and is smaller than this, then this has to go to infinity also. So that's what the idea is. Okay, so we need a function that's always smaller. So you can kind of compare it, kind of get rid of that 5. Right? So think about if you looked at this. So if you kind of got rid of that 5, you just look at 2n over n squared, which is really just 2 over m. Okay, so think about 2 over n, which is 2n over n squared, has to be smaller than if you had added 5 to the top, right? When you add to the top of a fraction, it gets bigger, you know, if it's positive. So, actually really anytime. Yeah, so this is bigger than this. This diverges, right? And then this is the nth term of a summation. This one diverges, and since this is bigger, this has to diverge also. So comparing it to 2 over n is what we want. Okay, which of the following series can be used with the limit comparison test to determine whether the series converges or diverges? Alright, so since we just have like constants and powers of n in the top and bottom, we're going to really just look at the terms that have the biggest exponents on the top and bottom. So the top is like 2 root n, which is 2n to the 1/2, and then the bottom is n cubed. Okay, so we're just really going to pay attention to those. So when n goes to infinity, this plus 5 on the top doesn't matter, you know, compared to this term that's going to infinity. And then also, when this n cubed goes to infinity, this 3n squared becomes insignificant. So you could really just kind of ignore this and then ignore this. So, okay, so we're going to look at when we're going to compare to something. And even for the limit comparison test, we can even ignore this too. The direct comparison test, you have to worry about these constants sometimes. But for the limit, you don't have to worry about that. So. Okay, so actually here, let's actually do that then. So let's not worry about the 2 even in the top. So we'll just worry about the root n. Okay, so we're just looking at root n over n cubed. Okay, and then this is the same thing as n to the 1/2 over n to the 3rd. Okay, and then you subtract exponents. 3 minus 1/2, really 1/2 minus 3 is negative 5/2. But that's just 1 over n to the 5/2. Okay, so that's the function that we're going to use to compare this with the limit comparison test. So you can kind of do that anytime you have powers of n, just powers of n, you know, no exponentials or logs or anything like that. So if you just have, you know, n to different exponents or roots of n, which is basically the same as roots to, or n to an exponent. If you just have that, you can kind of just do what we did. Pay attention to the biggest exponents on the top and bottom, right? And then simplify it. And then that's what you can use to compare with the limit comparison test. Okay, here, I'll do it down here real quick. I'll actually do the limit comparison test. Actually, no, I'm not. But that's what you do. We'll do it another time. Actually, I'll do it. What am I doing? What am I talking about? Okay, so let's do it real quick. Okay, so if you're actually doing the limit comparison test, I'll do it down here. So you look at limit and approaches infinity. Okay, and you're doing, you're just dividing these. So if you do this divided by the one we're comparing it to. So here I'll kind of write it out like this. Okay, and this is divided by. Change flip, keep the first fraction the same when you're dividing by a fraction, keep the first thing the same. Change division to multiplication and then flip the fraction. Okay, in this step also, I'm going to change this root n to n to the 1/2. I don't have much room to write, so I'm going to save space by not writing another line. Okay. Okay, if we distribute this n to the 5/2 to this first, or this numerator, do that down here. You'll get, and I'll, that's all right, actually I'll just do it so. Okay, and then n to the 5/2 times 2n to the 1/2 is 2n cubed. And the bottom will stay the same. Okay, and then now you're just evaluating this, the limit of rational function, or almost a rational function. So when you're doing that, you're just looking at the biggest exponents of the top and bottom. This is how you find horizontal asymptotes also. So you do top heavy, bottom heavy, same. So that's the same degree on the top and bottom. Degree is 3. So that means you divide by the coefficients of the terms with the biggest exponent. So this is like you do 2 divided by 1. Right? The exponent of the n cubed in the bottom is just 1, and that's 2. Okay, and the limit comparison test says if you get an actual number when you do this limit of these, the original and the one you're comparing to, after you divide those and you do the limit, if you get a number, not 0 and not infinity or negative infinity, then they both either converge or diverge. And then since we know that this one converges, since it's a p-series and p is greater than 1, that means we know that the given series will converge also. Okay, so that's C. Okay, the next one says, what are all the values of p for which this series will converge? So it looks like it's a p-series, but really this alternating series term, this term that makes it an alternating series, makes it so it's not an actual p-series anymore. So we won't do a p-series test. We won't think about the p-series test for this. We'll really think about the alternating series test. Okay, alternating series test says that this nth term part, really just has to be always positive, decreasing, and going to 0. So we just have to make sure that this p is some number that makes this term positive, which it will be, since n is always positive, always decreasing, and the limit as n approaches infinity will be 0. So, okay, so think about as long as p is like a positive exponent, think about, so really, we'll start out with the answer. So answer is going to be C. So as long as p is a positive exponent, you know, even if p was like 0.1, if you looked at 1 over n to the 0.1, this will always be decreasing, right? So this denominator will just keep getting bigger and bigger. You know, even if it was 1 over n to the 0.01, right? So this denominator, as n increases, this denominator increases, which means this fraction gets closer to 0, and n decreases. So, you know, whenever the denominator increases for a positive fraction, then the whole fraction decreases. Okay. So yeah, this will be decreasing, and it'll go to 0 since it's like bottom heavy. You can think of it like that. Okay, but think about if we look at like if the exponent was 0. Okay, so if the exponent was 0, 1 over n to the 0, this is really just 1 over 1, right? Anything to the 0 is 1. Okay, so it's almost like if this term was just 1, then it'd be the 1 times this is just this. So, and this bounces back between 1 and -1, so this will diverge, right? Because this value will, you're just being adding 1, add -1, add 1, add -1. So it won't approach anything. It'll just bounce back and forth between 0 and 1, I guess. Yeah, positive 1. Okay, so can't be 0. And then think about if the exponent was any negative number, whatever, -2 or something like that. So this is the same. It's just n squared, right? And so if this exponent's negative, it's just going to create this power, this, you know, positive power of n. And this will, you know, if that was this term, then this series would definitely diverge. Yeah, so p has to be just some positive number to make this series decreasing and going to 0. So, okay, which of the following conditions are necessary to conclude that the series from n equals 1 to infinity of an converges using the alternating series test? All right, so they're just really just what are the conditions necessary to say that a series converges by this test. Okay, so there's 3 conditions to alternating series test. You know, one of them says that it has to alternate signs, right? It has to be an alternating series in the first place. So that's what number 1 says. The terms an alternate in sign for all n greater than or equal to n, where n is some positive integer. So this little phrase here, let me highlight this. This really should be used more often for all these tests. Okay, so this is just saying we kind of, a lot of times teachers or books, or really the AP material isn't super formal with this, but like a lot of these things about these series don't have to be true for all the terms. It just has to be true for some term and then every term after that to infinity. And that's all this is saying. The terms have to alternate signs past some point, you know, past some term. It could be the 100th term and on, or the 1,000,000th term and on. So it doesn't really matter what's going on with the first, you know, 100 terms or 1,000,000 terms or trillion terms. It just matters from a certain point on, something has to be true. So in this case, it doesn't matter what the first, you know, n-1, capital N-1 terms. Doesn't matter what the series is doing for that. But starting with the capital nth term and on, when it's greater, when the terms are greater than that, then it has to alternate signs. So okay, so that's part of the alternating series test. Okay, so that has to be true. which of the following is a necessary condition? That's a necessary condition. Okay, next one saying is that the terms have to go to 0. Yeah, definitely. So if the terms don't go to 0, if they get closer and closer to a half, you're just going to be adding, a half every time. So it won't converge. You're really adding and subtracting a half. But okay, so but terms have to go to 0. That's just part of the test. Okay, and then this little phrase here. So so they're just saying, forget about the alternating series part. Just look at the positive values of these, the absolute values of these terms. So just saying every term, starting for all n greater than n, all lowercase n greater than capital N, when capital N is any positive integer. So they're just saying at some point and on, the terms have to be decreasing. So that's what this little phrase is saying here. Oops. So this little phrase is saying that the terms are decreasing. The absolute value of the terms are decreasing, right? Because it's saying that any term, if this is it's saying like the third term is bigger than the fourth term. And really, it's saying the fourth term is smaller than the third term. The 10th term is smaller than the 9th term. The 100th term is smaller than the 99th term, right? So it's just saying every term is smaller than the previous term. So that is really just saying that the terms decrease, or really non-increasing, because it could be equal. So let me be more formal. This is non-increasing. Okay, and that has to be true. That's what the test says. Okay, so this is just a more formal way of saying that the terms have to alternate signs to use the alternating series test. They have to tend towards 0. Limit has to go to 0, and they have to be non-increasing. So really, all three of those have to be true. Okay, the alternating series test can be used to check for convergence for which of the following series? Okay, so in the previous problem in number 6, we looked at the conditions that have to be true for a given series in order to use the alternating series test. Okay, so they have to, I'll kind of list them here real quick. So the terms have to be alternating. Okay, they have to go to 0. Okay, and this is, from a certain term on. Doesn't matter the first million terms or trillion terms or whatever, but just at some point on, they're going towards 0. And they have to be non-increasing. So either decreasing or staying the same. Okay, so which of these functions satisfy all three of these stipulations? Okay, so this one here, which is basically that 100, when n goes to infinity, this 100 won't matter. Actually, sorry, let's do the alternating first. So the alternating, it is alternating, so that checks out. Really, all of these are alternating because they have this alternating series term. Okay, so that number 1 will check out for all of these. So let's look at number 2. So do these go towards 0 if you take limit? Yeah, it's bottom heavy, right? You have an n squared in the top and an n squared in the bottom and in the top. Degree is 2 in the bottom and 1 in the top, so the limit will go to 0. So, and this is non-increasing. Yeah, this is really decreasing. Because this is basically the same as 1 over n. This 100 doesn't matter, and this will simplify to be 1 over n. So this will be decreasing always. So first one checks out. Okay, next one. So we know it's an alternating series, so that passes out. That passes that test. If you look at limit as n approaches infinity, so this doesn't equal 0. right? The degree on the top and bottom are both 1, right? The biggest exponent on the top and bottom is 1. If they have the same degree on the top and bottom, then you divide the leading coefficients, and so that's 1 over 100. So this, the limit as n approaches infinity, is 1 over 100. Okay, so it doesn't pass, so not that one. Okay, so next one. So it has some kind of weird description of this. So definitely it's all in an alternating series because it has the alternating series, -1 to the n plus 1 term. But then it says it's kind of it's a piecewise function that follows a different formula whether n is even or odd. So let's just plug in the first few values of n and see what's happening. Maybe first 4 values or something. Okay, so let's say we plug in for n is 1, the first term, then it's odd. So 1 is an odd number, so we'll plug it into this one. So 1 over 1 is 1, so the first term is 1. Kind of not paying attention to the alternating series part, just looking at the positive values. Okay, when n is 2, it's even, so we'll plug it into the bottom. So 1 over 2 squared is 1/4. Okay, if n is 3, it's odd, so that's 1/3. Okay, if n is 4, that's even, so plug in the bottom. So 1 over 4 squared is 1 over 16. If n is 5, plug it into the top. If n is 6, we'll plug it into the bottom. Okay, so notice these look like they are going to 0, right? These are gonna go to 0 since each one of these individually goes to 0. But notice that these are not non-increasing. These will always decrease and then increase, and then decrease and then increase, and then decrease, right? You can kind of see that, right? Definitely it decreases from 1 to 1/4, but 1/3 is bigger than 1/4, so this increases from one term to the next here, and then this decreases, right? And really just use the idea that if the numerators are the same, a bigger denominator means a smaller number. That's smaller, that's bigger, that's smaller, that's bigger, that's smaller. So, okay, so this is not non-decreasing, so it doesn't pass. So really just the first one. Okay, which of the following statements must be true about the series? From the summation from n equals 0 to infinity of an with positive terms. So they're saying an is always positive. And which of the following has to be true if the limit as n approaches infinity of n plus 1 over an equals L, some number, or infinity, I guess. So, okay. So, and now all the answer choices are talking about, what value we're just kind of looking at what values of L make the series converge. All the answer choices say the series converges if L equals a certain number or infinity. Okay, so basically they're just saying there's one of these values of L that this limit equals. There's only one value that makes this series converge. All the rest will make it diverge. Okay, so think about if L is a half. We'll look at kind of first 3 answer choices. So if L is a half, okay, so we're really kind of looking at answer choice A. So if you did if the limit as n approaches infinity of an plus 1 over an, if this equals a half, think about what that means. Okay, so that means that these, at some point when n goes to infinity, for maybe when n is a trillion and a quadrillion and beyond, it's saying that when you divide, the ratio of these terms is going to be 1 over 2. So it's like, maybe at some point this term is 10, which would make this one 5, and then this one's 5, and then this one's 2.5, and then this one's 2.5, and then this one is half that, you know. So like these always, this, you know, an plus 1 is just the next term after an. So it's saying every term after, you know, after its previous term is going to be half. Every term is going to be half the previous term. That's what this is saying, you know, or approaching at least. So if that happens, you know, every term is half the previous term, that's kind of acting like an exponential. Okay, so that's kind of like, not exactly, since it doesn't have to be exactly half, just has to approach a half. But that would almost be like if you were looking at the series, like from n equals whatever to infinity, of like 2 to the n, or sorry, not 2, of 1/2 to the n, like that. Okay, so notice like every term is going to be half the previous term, right? If n is 1, you give a half. If n is 2, you have a fourth. If n is 3, you have an eighth, right? Every term is half the previous term. And so we know that this converges because this is a geometric series when the ratio is between 1 and -1. So we know this converges. So we know if this is true, if every term is half its previous term, or approaching that at least, it's going to converge. So we know that that first one's true. So really that's our answer. Okay, we'll look at just real quick why at least B and C aren't true. Once we realize why B and C aren't true, especially why C isn't true, it'll be obvious why D isn't true. Okay, for B. Okay, now if limit as n approaches infinity of each term, the ratio of each term to the previous term is 2. So that's saying like when this term is 5, the next term is 10. And then when this term is 10, the next term is 20. When this is 20, the next term is 40, right? So it's just saying these terms, whoops, sorry, we got to do one first. Actually, that's, yeah, I'll do here. Let me fix that. Okay, if this is 1. Okay, sorry. So, yeah, so they're saying if this term is 5, then this is going to be 5. If this is 5, this is 5. So every term is like basically just a constant. So, so if every term is the exact same number, or you know, approaching the same number, then this series, these terms, if they don't approach 0, if they approach some number, some random number, then the series diverges, right? If this series is just an infinite, if the nth term is just a constant, if it's just 5, you're just adding 5 infinitely. So that's not going to converge to anything. That's just going to keep getting bigger and bigger. So, okay, and that's what this says. You divide any term by the previous term, and you get 1. That's just saying these are the same, or approaching to be the same. Okay, and if every term's the same, it's just going to keep getting bigger and bigger, or smaller and bigger and bigger if it's positive. So, okay, and actually it is key that it's positive, because these could be, actually no. Yeah, anyways, never mind. Okay. Okay, and then C, what I was kind of talking about at first. If this equals 2, then it's really obvious that this won't converge. Right? If this is 5, this will be 10. If this is 10, this will be 20. If this term's 20, the next term will be 40. Term's 40, the next term will be 80. Right? So you're just adding these bigger and bigger and bigger and bigger numbers. So that's just going to diverge, right? Just can't go to infinity quickly, even relatively, I guess. And then same idea. If this is infinity, if every term is an infinite amount larger than the previous term, then yeah, of course it's going to diverge. So, okay, so definitely A. Okay, they say which of the following series can be shown to converge by using the ratio test. Okay, first let's just look at a series. Let's just make sure we find a series that will converge. Okay, so this series won't converge because kind of forget about that 10. That 10, when n goes to infinity, that 10 won't matter. So you're just kind of looking at like, Okay, yeah, just looking at some series that like where the nth term will be like root n over n, and then this simplifies to be just 1 over root n, which is 1 over n to the 1/2. Okay, so this series will definitely diverge because it's a p series where p is less than or equal to 1. So, okay, so this diverges. So this series can't be shown to converge by any test because it diverges, right? Okay, the next one will definitely converge because you have an exponential in the bottom and a polynomial in the top. And there's an exponential growth function as long as the base is bigger than 1. Doesn't matter how big this exponent is, doesn't matter how close this base is to 1, as long as it's bigger than 1. This will always converge. So, exponentials will grow a lot faster than polynomials, at least, especially past some n value. So then this will definitely converge. So that's this is going to be the one, looks like. But okay, let's look at the other ones. So this one converges also. So, okay. And then this one converges also. Okay, so at least these last three converge. Okay, and then you want to use the ratio test. You want to use it for a lot of times when you're dealing with exponential functions and factorials that are within functions. But a lot of times it will be inconclusive for rational functions like in D, and then ones with logs, and it's rational besides that. You have an n squared and a log. So it'll be inconclusive. A lot of times when you use ratio tests for functions like these, I think really any time you use it for a rational function, it'll always be inconclusive. But even for these types, it'll be inconclusive. Okay, so I think B is going to be our answer. So let's look though. Okay, so let's test answer choice B. These we just have to test the answer choices. And this will be practice with the ratio test. Remember, the ratio test says that as long as the absolute value of the n plus first term divided by the nth term, if the absolute value of that is less than 1, then it converges. If it equals 1, it's inconclusive. So that's going to be the main idea for these. Okay, so let's say if we do limit as n approaches infinity, and since these are all fractions, if we do the nth term divided, or the n plus first term divided by, each one of these is the nth term. So if we take the n plus first term and divide it by each of these fractions, I'm just going to multiply it by the reciprocal right away, because that's what just to skip that step. So we're going to do the n plus first term. Just substitute n plus 1 for all the n's. And then times it just by the reciprocal right away. Okay, so these cancel just to be a 10 in the bottom. Okay, and actually here I shouldn't have written that. Okay, so this is like, since there's a 10 in the bottom, I'm going to pull out a 1/10 just to get that out of there. And then this is really just limit and approach to infinity. And we don't really need that absolute value because these n's are always positive. But okay, and then since this is equal to 1, this limit is equal to 1, and that's because if you FOIL this out, you'd get n squared plus blah blah blah. So this is like the same degree on the top and bottom, and then you divide these coefficients and you get 1, and then times 10. So this is less than 1, so that's why this checks out. Okay, so we know that the answer is going to be B. Okay, so let's just look at C and D real quick. Okay, so same thing. I'm going to do the n plus first term. reciprocal of the given. Okay, so you can see this is going to equal 1 because think about this n squared over n plus 1 squared. When you divide these, when n goes to infinity, these are going to approach 1 for sure. You know, if you just split up, you could actually formally, here I'll show the kind of formal work that you would do. And you're kind of you're allowed to distribute distribute limits to things multiplied, and sometimes divided also, but maybe most of the time divided. Okay, we can kind of write it like this. Okay, and then each one of these separately will approach 1, because you can kind of just tell, like, you know, as this n goes to infinity, this is going to be, you know, ln of 1001 over ln of 1000, ln of 1,000,001 over ln of 1,000,000, right? So these are going to just become closer and closer to each other, and so it's going to get close. This whole fraction is going to get closer to 1. It's kind of the same idea here, but you could even think of this as the same degree on the top and bottom, right? You'd FOIL this, you get an n squared in the bottom. Divide the leading coefficients, which are 1, and that would be 1. So this is really just 1 times 1, and so that's 1. So which means that's inconclusive, so you can't use the ratio test. Okay, same idea for the last one. For D, if you plugged in n plus 1, that top becomes n plus 2, n plus 1 plus 1. Okay, times the reciprocal. Okay, and then the same idea, if you split this up just like we did the last one, the limit of these two divided, n plus 2 over n plus 1, that'll go to 1, and then these will go to 1. You could even just really FOIL this. You'd get an n to the 5th in the top and bottom, and that'll be 1. So those are inconclusive, so you can't use ratio test for those. Okay, so these you can't use ratio test because they're inconclusive because they equal 1, and then A, you can't use it to show that it converges because it doesn't even converge in the first place. So, okay, which of the following series converges? Okay, so we'll just go one by one. All right, so the top one, so you know, we can kind of maybe even rewrite it. Okay, this will be like, you know, this n exponent will distribute to the top and bottom. So 1 to the n is just 1, and then the bottom will be e to the n. So this is 1 over e to the n. And this is the same thing as 1 over e to the n times n. That's n over e to the n. Okay, I'm going to use kind of informal tests. We could use ratio test to show that this would end up equaling, what would it equal? 1 over e, which is less than 1. So we could show by ratio test that this converges. But really just use the idea that if you have an exponential in the bottom where the base is bigger than 1 like this, and you just have any polynomial in the top, doesn't have to be, it could be have a huge exponent even, it could be n to the 1,000,000th. But if you have an exponential at the bottom and any power of n in the top, then this is always going to converge. So definitely first one converges. Okay, and it converges because you have, I'll write it this way, polynomial in the top and exponential growth in the bottom. Okay, so that's converges. Okay, the next one has factorial in the top and exponential in the bottom. That's going to diverge. So factorials, you know, once n gets to a certain value and beyond, factorials will increase a lot faster than any exponential. It doesn't matter how big the base is, because, you know, you can see like for this one, once n gets beyond 100, once n gets to be 100 and beyond, every increase in n will, for the factorial, will increase it by a number bigger than 100. For the bottom, every time it increases by 1, the bottom just gets multiplied by exactly 100. And so this will just be increasing by something bigger and bigger than 100, and this will just keep getting multiplied. The bottom will keep getting multiplied by 100 exactly. And so that's why factorials go up a lot bigger than exponentials. Usually exponentials will be bigger than the factorial for a while, but at some n value and beyond, the factorial will be bigger and will grow faster than the exponential. Okay, so that's why this will diverge. So it diverges because anytime you have factorial over exponential, okay, this is diverge. Okay, bottom one, got factorials in the top and bottom. The bottom, this is definitely going to be, oh wait, let me think, actually, sorry. Okay, yeah, actually this will definitely converge. Okay, it's kind of a weird little function. So the top is like n factorial squared, so n factorial times n factorial, and the bottom is 2n factorial. Okay, so I don't know, when I was thinking about it, when n, just kind of for certain values of n, I was thinking about like when n was 5, let's say, this is 10 factorial, and then this will be 5 factorial times 5 factorial. And then, within 10 factorial, that's 10 times 9 times 8 times 7 times 5, all the way down to 1, right? So this at least includes 5 times 4 times 3 times 2 times 1, right? And then this is 5 times 4 times 3 times 2 times 1 twice. So that kind of, the 5 factorial will cancel out with some of the 5, the 5, 4, 3, 2, 1 from this one. And then this, I don't know, anyways. But let's just do ratio test. There is a way to think about it informally, but let's just do ratio test for number 3. Okay, so do limit n approaches infinity. Okay, we don't need absolute value since this is always positive. So actually, yeah, if we're doing using ratio test for interval of convergence, we would do it because x could be negative, but we don't need it for this one. So okay, so we'll do the n plus 1 version of this, and I'm gonna, instead of n factorial squared, I'm gonna write it out as n plus 1 factorial times n plus 1 factorial. Okay, and then the bottom will be, I'm going to say 2n plus 2 factorial. Okay, so yeah, if you substitute n plus 1 for this n in the bottom, you distribute the 2, and so that'll be 2n plus 2. And the top is just n plus 1 factorial squared, which is n plus 1 factorial times n plus 1 factorial. Okay, we'll times that by the reciprocal, which is 2n factorial. And then this is going to be just n factorial squared, which is n factorial times n factorial. All right, and these are kind of nice to simplify. So, so like that n factorial and the n plus 1 factorial cancels to just be n plus 1. Same with those, cancel to be n plus 1. Okay, and then these cancel to be 2n plus 2 times 2n plus 1. Okay, that's kind of a weird one. Okay, and then now, if you look at as n approaches infinity, you have this in the top, that's like an n squared when you FOIL, and the bottom is a 4n squared, so this will equal 1/4. Okay, which is less than 1, so that converges. Okay, yeah, so then this is 1 and 3, so this is answer choice D. Okay, consider that series from n equals 1 to infinity of -1 to the n plus 1, so an alternating series of an, and then that an is greater than 1 over n. Okay, for all n, and the sequence AN, sequence AN, just the list of the terms of that sequence decreases with limit equal to, with limit 0. Okay, which of the following statements is true? Okay, so the fact that this series, first off, this whole series is an alternating series. And then since this nth term decreases and the limit 0, that means this is going to be, this series is going to be convergent. So we know it definitely doesn't diverge. Yeah, and it's definitely not D. We don't know yet if there's enough information to determine whether it converges absolutely or conditionally yet, but it definitely doesn't diverge, and there's definitely enough information to know that it does converge. So it's not C or D. So we just have to figure out if it's absolute or conditional. So if this series on its own, kind of forgetting about this alternating series part, you could think about the absolute value of this. If this series converges also, this alternating series converges, but if the series on its own without the alternating series part, if it converges, then it'll converge absolutely. If this series AN diverges, then this series will converge conditionally. So okay, and it's kind of obvious, this, since converges at least conditionally because it passes the alternating series test. But this term AN diverges, you could think about because of the direct comparison test. So we know that 1 over n diverges because it's the harmonic series, or P series where P is equal to 1. So we know 1 over n diverges. If AN has terms that are bigger than that for each n, then AN diverges also, right? If you have a series that diverges and another series with bigger terms, it'll diverge also. Okay, so the fact that this alternating series converges, but the series on its own diverges, okay, that means it converges conditionally, so that's B. Okay, next one. Which of the following series converges conditionally? Okay, they're all alternating series. And okay, it's definitely not A. Those terms, just the absolute value of those terms just get bigger and bigger. So we'll think about the alternating series test. Would say that these diverge, right? The terms 3/2, the 9/4, 27 over 8, like these terms, the absolute value are just getting bigger and bigger. So they don't go to 0. The terms themselves have to go towards 0 to converge, so it's definitely not A. Okay, let's look at the next one. So, let's see. So definitely the terms go towards 0 because exponentials grow slower than factorials. When x is 100 or when n is 100 or a million or something, then that 2 to the n won't grow as fast as n factorial. So this will definitely at least converge conditionally by the alternating series test. Terms go to 0, they'll be decreasing, but this converges absolutely because the series on its own, the series on its own without the alternating series part would be like, would be 2 to the n over 2 to the n over n factorial, like that. And so that definitely converges, right? So it doesn't even, we don't, if the series itself converges, then the alternating series, if the series without the alternating part, if the series on its own converges, then it'll converge absolutely. So this is absolute. Okay, this is diverges. Okay, the next one, we can see the series on its own is really just 1 over root n. Okay, but first off, yeah, so it's 1 over root n. So then this is decreasing and goes to 0. So this alternating series will be at least conditionally convergent. And then this series on its own diverges because this is a p series where p is equal to a half, right? Square root is a half. And so this series diverges. So the overall series converges, the alternating series converges, but the absolute value of the terms diverge. So this is the answer. This is conditionally convergent. This is absolutely convergent. Okay, and then let's look at the last one. So same idea. These terms, you know, the general term is 1 all over, actually it's really, we'll write it as 1/5 to the m. So this is a geometric series. You know, even on its own, without the alternating series part, this converges because it's a geometric series. So we don't even have to look at the alternating series part. This is absolutely convergent. Okay, so which one's conditionally convergent? And so that's C. Okay, so which of the following series is absolutely convergent? So if we only want to know which one, if they're absolutely convergent, we'll just forget about the alternating series part, because to be absolutely convergent, the absolute value, you know, without the alternating series part, has to be convergent. And if that's convergent, then the alternating series itself will be convergent every time. So we'll just look at the absolute value of these terms. Okay, so kind of forgetting about the alternating series part, the nth term, or the kth term, is 1 over k. So that's divergent. So that means it's definitely not absolutely convergent. We're looking at the nth term or the kth term to be convergent itself in order for it to be absolutely convergent. Okay. So the next one is definitely divergent. You could do direct comparison test with 1 over k. So since 1 over k, you know, the series k equals 2 to infinity of 1 over k, since that diverges, it's a p series or p equals 1, then when you divide it by a number bigger than 1, which it will be for value when k is at least bigger than 2, so you're you know, this, you know, for values of k bigger than 2, this will be this one's not so obvious, at least to me. I don't know, maybe it's for some people, but not obvious right away if you haven't seen this before. I would have first thought that this was convergent, absolutely, but this is divergent. We could compare, this is divergent, and if you did limit comparison test and compared these, it would show that if you do limit comparison test, that'll equal a number, that'll equal 1. And so then, since this is divergent, this will be divergent also. So this is actually divergent, this one. So here, let me write these. So this is conditionally convergent. This is actually just straight up divergent. Okay, next one is definitely going to be the absolutely convergent. This is going to be the answer. Okay, first off, this cosine is just some number between 1 and -1. So you can almost treat it like a constant. And so, you know, and this plus 1 doesn't matter. So you can even just compare this to 1 over k squared. And so 1 over k squared converges, so this converges. So, okay, and then the last one will converge conditionally, because if you forget about the alternating series part, but if you look at k k squared plus 1. Kind of get rid of that plus 1 in the bottom. You get k over k squared, which is really 1 over k. And so since this diverges, the part without the alternating series will diverge also. But the alternating series itself converges, since this term will be decreasing and go to 0. And so yeah, the overall alternating series converges, but the absolute value diverges. So this will be conditionally convergent. Okay, so the C is the only one that's absolutely convergent. Okay, so if the partial sum with 3 terms is used to approximate the value of this convergent series, what's the alternating series error bound? Okay, so if you're going to use the first 3 terms of this series, you can see this series starts when n equals 3. So the first 3 terms will be when n equals 3, 4, and 5. Okay, so we'll use the first unused term is when n equals 6. So that's what we'll do. Plug in 6 into that. So you get 6 over 2 to the 6, which is really 3 over 2 to the 5th. Divide both top and bottom by 2, which is 3 over 32. Okay, and that's it. So that's A. That one's kind of quick. Okay, so first this is testing the idea of how partial sums and are related to the terms of the sequence themselves. So first let's just make sure we get this one little concept before we get into this problem. So think about, like, if you did just kind of, I'll do the formula first. You could say the nth term is always equal to the s, or the nth partial sum minus first partial sum. Okay, and this is best seen when you're doing an example. So I'm just going to do an example right away. Just doing one example, you'll see why this is true. So think about, let's say you did, let's say you're just looking at even like the 4th partial sum. Let's say n is 4. So this is saying that A4 is equal to S4 minus S3. Okay, so think about why that's true. So S4 is the sum of the first 4 terms, A1 plus A2 plus A3 plus A4. And then S3 is A1, first 3 terms, plus A2 plus A3, right? So think about, if you subtract these, if you do S4 minus S3, subtract these, you can just see everything cancels and you're just left with A4, right? So if you subtract the sum of the first 4 terms with the sum of the first 3 terms, you're just going to be left with the 4th term. Okay, so let's get into this problem now. So they say the alternating series, some alternating series, converges to S. Not sure exactly why they have this stipulation. This stipulation just says, 0 is less than or equal to these, so it's just saying that these are positive, or 0, I guess. And then this is saying that the terms are decreasing, right? The n plus first term is less than the nth term, so any term is less than the previous term. So this just says it's decreasing and positive, or non-negative. And that just has to be true in order for the alternating series to converge, I guess. So they're just restating that, I guess. I don't know. Okay, table above shows the values for the partial sum of this series. And they say S8, the partial sum, is used to approximate, the 8th partial sum is used to approximate the value of the actual sum, infinite sum. What's the alternating series error bound? Okay, so that means we're going to use, if we're using the first 8 terms to approximate the value of the infinite series, that means we're going to use the 9th term. The 9th term is going to be the error bound. So I'll do the work up here. So that means A9 is our answer. That's the first unused term. S8 is adding up the first 8 terms, so it's the ninth term that we're going to use as the alternating series error bound. Okay, but these aren't terms themselves, right? Notice this says SM, so this is the sum of the first 7 terms, sum of the first 8 terms, sum of the first 9 terms, sum of the first 10 terms. Okay, so we've realized from the work down below that this is really just S9 minus S8. Oops. Okay, so it's really S9, you can see from the chart is 0.459. S8 is 0.157. So if you subtract these, you get 0.302. Okay. Okay, and that's it.